Okay, so good morning, everyone. We are very happy to welcome here today Professor Ulrike Tillmann. Ulrike is a professor at Oxford in the Faculty of Norton College, and well, she has did her PhD in Stanford and has ever since had a very, very successful mathematical career. In 2004, she had the Whitehead Prize from the London Mathematical Society, and is also a fellow of the Royal Society. And I think this year she has been made a fellow of the American Mathematical Society. And well, mathematically she has made huge contributions to the to the modular space of algebraic curves. So, okay.
So thank you very much, Carmen, and all the other organizers for inviting me here. It's a great pleasure to be here. For once, I thought I was organized and sent in my title relatively early, but then I looked at the people attending and the topics presented, and I thought, well, that's actually not quite right, so I changed my title. I'm afraid that's the problem about being organized. So what I want to talk about today, I mean, one reason why I changed the title, because I saw a large category theory group here and also mathematical physics. So I thought this topic might be a bit more suitable. So what I want to talk really about is some classical theory, and I start off in some sense about some classical topological theory, or manifold theory. And then I'll look at some new ways of cobordisms. New ways to look at cobordisms, really, in the form of topological field theories. And then I try to bring, to combine the two a little bit. And you will see actually the title or the topic has much to do about configuration spaces. Configuration spaces not just of points but also of manifolds in higher dimension. So let me start then. So I'm a topologist, and one of the big problems in topology and geometry is to study manifolds and to classify them. So manifolds of dimension d, it's just something that looks locally like r to the d, and if you allow a boundary, then on the boundary, of course, it might look just like part of r to the d, namely the upper half plane and r2. And we say a manifold is closed if it is compact and has no boundary. So the fundamental problem really is, can we classify these compact, smooth manifolds? And then you have to say up to what? Up to diffeomorphism, up to homomorphism, etc. I will be mainly interested in up to diffeomorphisms. So manifolds come in different sorts of flavors. And let me just introduce very briefly the flavors that I might be interested in. That's a non-orientable. So basically what I just said there is the definition of the manifold. I don't have any extra structure. I might want my manifolds to be orientable. So if you're on a surface, you might want to know what's the upper side and what's the lower, below, up on top or below a surface. And then finally, a slightly more complicated or more rigid structure is a framed manifold. So then, at every point in the manifold, I want my tangent space, I want to be given actually a basis for that tangent space. So in other words, at every point, I not just know it looks like r to the d, but I have a very specific map given by a chosen set of bases. So those are the sort of things I want to look at. Okay. So here examples. Of course, when d is less than 0, there's only one manifold, namely the empty manifold. when d is 0, it's already an interesting case. D equal to 0, what is a compact manifold in that case? It's just a bunch of points, finitely many points. D1 is also very clearly understood. What you can have is just finitely many circles or intervals for compact manifolds. And D2, you probably have seen pictures of surfaces. Here, a double donut, that's an orientable surface, and we know that orientable surfaces are completely defined by their genus, how many holes I have, and possibly if I have boundary components, if I have boundaries. But of course I also have the non-orientable ones, so these are the orientable ones. And non-orientable one, the typical example of course, is the Möbius band. And that of course is of genus 1 with 1 hole. So we completely understand the two-dimensional case, and then the three-dimensional case only very recently in some sense has been settled with the work of Perlman and more recently Alborn and so on. So in higher dimension things are rather more complicated, and indeed to some extent we know we can't classify manifolds because any group can appear as a fundamental group of a manifold, and they are not really classifiable. They're not even somehow you can't even list them. So there is a bit of a problem in that sense. Now, an old idea from going back to the 50s is actually to somehow have a relationship on manifolds, and so that we can look at them in classes. So this is a cobordism relationship. So let me just draw the second surface there. The idea is you have one manifold M1 and another manifold M2, and if the union of them is the boundary of another manifold, W, then we declare M1 and M2 equivalent. So that's a very nice relation because it's an equivalence relation. So let me just briefly say, what do we need for an equivalence relation? Well, you need reflexivity. Reflexivity, well, if you have a manifold M here, well, it's related to itself by just looking at the cylindrical cobordism. It's also reflective. This M1 is related to that M2, but if I just turn around the picture, then we see that M2 is related to M1. And finally, we need also transitivity, and that's the picture up there. If I have a cobordism between M0 and M1, and another one between M1 and M2, I can glue them together to give me a cobordism, which now relates M0 to M2. So it's an equivalence relation. But furthermore, it's a very nice equivalence relation, namely on the set of equivalence classes. It's a very, let's see, the symbol here is actually not just a set, but you can give it a group structure. Okay? So what is the group structure itself? It's just the disjoint union. Okay? I have two manifolds M, and here's my manifold M, and I have a manifold M dash. Then, of course, the union is again a manifold of dimension d-1. And why, so what is the inverse? Well, first of all, we should ask then, what is the unit? If disjoint unions are product, then of course the empty set is the unit. So if we want to have M, if we are looking for the inverse of M, well, then we need something that relates. So if M dash is the inverse, then we need something that relates these two to the empty set. In other words, we need some manifold that has those two things as the boundary. So if we just take here M bar, that's M with the reversed orientation, then, and think of the cylinder, then that tells us that actually M and M bar actually are inverse elements. And finally, not only is this a group, we can even give it a multiplication, and the multiplication is given by cross product. Yeah? So, of course, when it takes a cross Cartesian product, then we better take the collection of all these cobordism groups, because, of course, we are going to increase our dimension when we take Cartesian product. I won't use very much the multiplication, but I think it is important to understand that we have equivalence classes and indeed a product and inverse. Okay. So let's see an example. Now I'm thinking about the oriented case. So what is this group in dimension 0? Of course, I only have points, and the points come with an orientation. So I might have plus and a minus orientation. Now if I have 2 points with opposite orientation, then they're cobordered to the empty set. So in my group, these two things actually are equivalent to 0. And of course, when I have a bunch of pluses and a bunch of minuses, then I can always pair them up like this. And what I left is the ones that are not paired, and they're either all positive or all negative. And that gives me an identification of these with Z. So if I have n positive and n negative, then the equivalence class they give me is actually m minus n in Z. And similar with the next group. So we are now thinking, I want to explain why actually the cobordism group of dimension 1, the oriented group, is 0. It's a trivial group. Why is that? Well, I just have to tell you that whenever I have a bunch of circles, they are actually the boundary of a surface. But that's sort of clear, right? The boundary here, this tells me these 3 circles are equivalent to the empty set, which is our unit. So that group is trivial. What about in dimension 2? Well, I drew the same surface as here. Given a closed surface like that, I need to tell you it is the boundary of a 3-dimensional manifold. But the 3-dimensional manifold is already there. Just fill in this double donut. And actually think of it as a donut rather than an inner tube. Or then you get actually something solid, which is 3-dimensional, and it has this as a boundary. So all orientable surfaces are actually the boundary of a 3-manifold. And again, our group, cobordism group, is rather trivial. And you might wonder what happens in the non-orientable case. And it's a bit more tricky. It turns out to be Z mod 2. It's not a very difficult calculation, but but as soon as we go to the higher groups, it becomes very complicated to understand what these cobordism groups are. So it came as it's a great theorem by Tom in the 50s, that he was able to identify these cobordism groups with something that looks a priori rather more complicated. So I'll explain what this is. First, but the important thing to note is really that, well, we take homotopy groups of some space. And it was, I'll describe the space a little bit in a moment, but the space in particular, the homotopy groups, are finitely generated. So that tells you immediately something about the cobordism group. Before, we had no idea what this thing was. We started off with these manifolds that are completely bulk B's, basically. And now we know by Tom that the co-optical they're actually forming a finite generated group. So what is this space? Again, the ingredients are quite simple, so it might be worth looking at it. Let's start actually with this GR plus NK. What is it? It's a space of end-planes, oriented end-planes, in Rn plus K. So, for example, if you take projective lines in 1 plus K dimension, that's our first GR plus 1K. Right? So projective space is just one example. Now, such a space, of course, has a canonical vector bundle, because every plane, I can think about the points in that plane, and this space U and K is just a collection of all the planes with the points in them. So this defines for me a very canonical n-dimensional vector bundle. Okay, and then what else do we need to do? We have this vector bundle. I compactify, one-point compactification, and then I look at maps from the sphere into it. That's a standard construction, and we take limits. Okay, that's basically it. So maybe to just give you a bit of feeling, if you haven't seen it before, it's really quite confusing maybe at first. So what happens, for example, for the zero-dimensional case? Basically, what this theorem tells us that this Z somehow I should be interpreting as pi naught of this huge space, the connected components of that space. Or in other words, any zero-dimensional manifold like this should give me a point in this space. Or it should give me, in other words, a map from some Sn into one of these guys. Right? And this is actually the definition of the map here. So let me just write it down. Let's start with some collection of all positive oriented points sitting in Rn. Now I look at these points, that takes a plus away because it's confusing, and just draw little balls around them. Now, this sits in Rn, but if I compactify Rn, that of course gives me just an Sn. So this picture, now I take actually to the batch of these, I collapse everything outside the balls, and what I get is really just m copies of Sn, one for each point, one for each ball. And finally, I can map, of course, this, so-called fault map. Every Sn gets identified with Sn, but this Sn I now think of actually as Un0 compactified. So what is that? According to our definition, I look at the Grassmannian of n-dimensional n-planes in Rn. Well, there's only one. Okay, so this is actually a point. And now Un is the plane together with all its points. So that means that Un0 is actually just that plane, R to the n. So if I compactify that now, I just get my Sn, and of course, now I can, of course, map this. This is one of these. Let n and k go to infinity, and I get something in here. Now, what is that? So I'm looking for an integer, but here is an integer. I have a map from Sn to Sn, and that has a degree. And that degree is precisely what I would get when identifying this group here with pi naught of MSR. So you might ask yourself, well, but what happens with the minus points, etc.? What happens with the minus points? Well, in that case, I would have a different orientation of these balls in the fold map, and the fold map would take actually not the Sn to itself, but it would map it by a degree minus 1 map. And so we get the right identification. Okay. So what does Tom's theorem say? Tom calculated these things, and in particular, I mean, that's a wonderful thing. I said that these spaces are actually relatively easy to understand, and here's actually sort of a proof of it. Namely, you can calculate the rational cobordism group, or we can, in other words, calculate the rational homotopy groups. Let me just go through it very quickly so you realize it's not very deep or more complicated than you might know. Basically, this calculation you can find in Milner's Stashet, for example, standard textbook. So you take this group, tensor with Q, that's by definition this complicated expression, because the spheres, I'm looking at homotopy groups, spheres are compact, so really I'm not, as long as n and k are large enough, I can just restrict myself to one of these things. Now, of course, maps from Sn into something just shifts my homotopy groups. That's the second line, so that's a very trivial one. And the next step is deeper, namely I'm using something that the homotopy groups rationally are the same as the homology groups in a range of degrees depending on the connectivity of the space. So this space is at least n connected. So this equation will hold for all star less than n. So it's just a range of degrees. And that's the theorem by Serre. And finally, the last step is just what we call Tom isomorphism theorem. So it's a very straightforward calculation, and we understand this relatively well. Okay, here's Tom. Just to introduce him. And let me go back one step. So I want to now say something about configurations. Where do configurations come in? And they will appear later on again. You see here we started off with one specific collection of points in Rn, and we constructed from it a specific map. But of course, we can do this for every such collection, and we get a slightly different map. So up here, I denote the space of all this collection of points by CMRn, that's a configuration space. And of course, for every such collection, we just saw we have a map from the n sphere to the n sphere. That's this here, and it's of degree n. So Graham-Siegel proved that this is actually an approximation, and more precisely, this map here is an homology isomorphism in certain degrees. So these spaces, configuration spaces, are particularly interesting in for R2, for example. This gives you a classifying space of the break group. I know that we're going to talk about that. And it tells us that the homology of this break group in a certain dimension is just the same as homology of this double loop space. And when we have R infinity, then actually we have classifying space of the symmetric group. So, if you felt like this, you've lost me, this is the time to tune in again, because it's a different topic, really. So we are coming to, we left the classical cobordism thing, and are moving now to a new way of using cobordism that was introduced coming from topological field theory. So, what is topological field theory? What we do, we start with a category, the discrete cobordism category, and we take the objects to be our closed-oriented D-1 dimensional manifolds. Okay? And we have morphisms. The morphisms are precisely our cobordisms. So, for example, here we have object M1, object M2, and W dash is a morphism. That's how we think about these things. And composition, of course, is just given by gluing. So if I have another cobordism from M2 to some M3, I will just glue them together. So what is the topological field theory? It's a factor from this into V, which is vector spaces over C. And there are conditions on this, namely I want the disjoint union of manifolds to go to the tensor product. Okay. Now, we know what the unit is for disjoint union. That's the empty set. And we know what the unit is for tensor product. That's just the ground field. So let's take it back to be C. So we know immediately that this assignment has to take the empty set to C, just because the unit has to go to the unit of this, because F is supposed to preserve the product structure. Okay. So there's I've studied topological field theories, and I guess the formalization that I just gave axiomatization is really due to Artier, who I should mention here in Edinburgh at least. Okay, so what is the motivation? Artier, after all, is a geometer topologist, and he was particularly interested in these topological fields in order to get invariance of manifolds. How do you get an invariant of a manifold? Well, take W, think of it as a closed manifold. So let's think again about this surface. This is our W. And we can think of it as a morphism from the empty set to the empty set. Now, the assignment gives us now a map from C, a linear map from C to C. A linear map from C to C is just a number. So if the topological field theory actually gives us a number which is by definition only invariant, it's an invariant of the topology by different. Let me actually make that a little bit clearer. Why is it depending only on the topology? Because I didn't say that very carefully here, so on purpose. The morphism here, the cobordisms here, we don't just take all of them. At this stage, we are taking only those, we identify them to cobordism if they are diffeomorphic by a diffeomorphism that is the identity on the boundary. Okay? So that's an equivalence relation on the morphism space. That's the equivalence relation there will make sure that this F is actually a topological invariant. Okay. Now, what is the physical inspiration? Why do you think cutting a manifold up into cobordisms should help us? Well, quantum field theory somehow is supposed to be local. Everything is determined by a local. Okay? So let me, I'm not sure which board to use really. So the idea is we have again, let me redraw my picture, and the idea is that everything is local, so in a way the manifold should be determined, or the field theory should be determined by what happens in each of these strips. And so if we understand each step, then we should be able to understand the whole thing. But in a way, there's no reason why we should just cut in the horizontal direction, sorry, vertical direction. We should also be able to cut possibly this way. Right? And if we start with the surface, cutting just once in the horizontal direction left us with circles, with something one-dimensional. If we also cut our manifold in the horizontal direction, then we end up with something like this, which is, well, a manifold with corners, you might say, but in particular what we see is here that we have 2 points and cobordism between them, and another 2 points and cobordism between them. And here we have 2 points and null points and a cobordism between them. So what we are doing now is really then the surface is a cobordism between cobordisms. That's how we want to interpret it. So you're building up a 2 category. We're starting with objects, just the points. Then we have morphism between these objects, which are the cobordisms, which are one-dimensional cobordisms. And now we have 2 morphisms, which are surfaces. If you haven't seen higher categories here, basically you just need to think about a set is a 0 category with no structure. A 1 category is a set where you have a composition. And a 2 category, and in the basic sense, is a set where you have 2 compositions. Okay? And that set of the highest level of morphisms, the 2 morphisms here, is a set, and I compose them in 2 directions. Namely, I can add things in this direction, glue in this direction, or I can glue in this direction. So I have 2 directions of composition. And I leave it to you to generalize to 3 now, right? You take a 3 manifold, cut it in 3 directions, and now you have something cubical, and you can compose it in 3 directions, and 4, and 5, and so on. Yeah? So that's a very simple way of thinking of a 2 category in this case, or a higher category. So when we have a default category, we just do exactly that with our cobordism category. We get this extended category, and we now can map that. We can think of some generalization of our vector space category, which has to be also some category, and can now study functors from our d-dimensional cobordism, default cobordism category into this more complicated analog of a vector space category. Okay. And the idea, oops. Yeah. So when we said in physics that everything was determined by what happened at that point, that is now formalized in for topological field theory in the Bayes-Dolan cobordism hypothesis. Namely, it says that the extended field theory we just defined is completely determined by what happens on a point. Okay? So what, very briefly, what does this do in dimension 1? All right, 1-dimensional field series. So we only cut down to the 0-dimensional side. So actually, we are dealing with just with a category. So that's something we should be able to understand, right? So we are. Our objects are points, plus and minuses, and we have these different cobordisms that we might have. So what can we say? Well, the first one is an evaluation, well, E functor, right? It takes what I assign to the positive point, which is a negative point, and it maps it to C, and vice versa. I get an E star to B dash tensor V, and so on. The point is, this S formation tells us actually that V has to be finite dimensional. Why is that? Because if I try to see this, I take a V, and then I apply the identity, and then I apply E star, but what is E star? It has to be some finite sum of EI star tensor EI. It has to be a finite sum, of these things. And finally, I then evaluate. So I contract these things, and I get a sum of the EI star applied to V tensor EI. And whatever I do, I end up with something that is finite. It's a finite sum, and everything, every V, you see, this composition, because everything up to topology, and this is just a straight line, so a cylinder, which has to be the identity. So whatever we do, this V we can write as a finite sum of basis elements. And since every V can be written like that, our V has to be finite dimensional. And finally, the circle will actually give us the dimension of the vector space. Okay. So in this case, we clearly see that whatever we do to a point, it's the dimension of the manifold that's really classifying this. So the question then was, is it really true? Is the cobordism hypothesis really true? Is everything really determined by what happens on a point? And the way we looked at in the formulation of Artea, we identified cobordism at the highest level if they are diffeomorphic. So it was really a discrete category. Now it's very hard to work with discrete things. They look simple, but it's actually quite difficult. So in this case, we really have to have an enrichment. It makes the problem more complicated to actually get a solution. But it's not that much more complicated. So here's another configuration space, if you like. It's a configuration space now of all cobordisms in some Rn. So rather than just looking at points, which I could if d is equal to 0, but more generally, I look at cobordism between, I have m0 and I have m1, and rather than just taking one specific copy of a w between them, I let this w wobble in my Rn. Yeah? So it's a space, it's a moduli space, if you like, of topological moduli space of these cobordisms w. And topologically, these morphism spaces, rather than being discrete, rather than just having a point for every diffeomorphism class, we now have actually the classifying space of the diffeomorphism group itself. Okay. So grant me this enrichment, we still can look at cobordism categories, enriched cobordism categories, and functors to some default symmetric monoidal category. This was our generalization of vector spaces. And indeed, the theorem, there's now a theorem by Hopkins and Lurie for n equal to d equal to 2, and Lurie more generally, that any extended TQFT is actually determined by what happens on the point. Now, I sneaked in a little FR here, and that is the theorem is most easiest to state for manifolds which are framed. There's an analog for manifolds which are orientable or non-orientable. Remember, a framing was just at every point I have also a basis for the tangent space given. Right? So in particular, the tangent space has to be trivializable, etc. But so let's think of this as just a complication in order to write the theorem, but there are analogs also for the orientable, non-orientable case, which are slightly harder to say. Okay, okay, so I want to come back now. So we had the story with Tom's cobordism theory, and now we have the topological field theory, and it seems to be all in both directions, all nicely settled, but is there any connection? And the answer is yes, so let me come to that part. So this is now part 3. And again, if you lost me in the last 15 minutes, this might be another time you can tune in and get something new. So, how does a topologist study categories? Well, a topologist studies spaces, so the thing to do is to associate to your category a space. Okay? It's a very well-known construction, actually going back again to Graham Siegel. And what do we do? I take a category, and the category has objects and morphisms. So for every object, I just give myself a point. And for every morphism, I give myself a little interval. Right? And when I can compose two morphisms, oops, I lost my point. If F can be composed with G, then I give myself a little triangle and call the on the opposite side the composition, FG. So you can see I can now go on, give myself a tetrahedra for three composable things, etc., etc. And I glue these bits together by identifying those bits that have the same name. So this point A gets identified with this, and of course this edge gets identified with this, and so on. Yeah? So I glue things together, I get a nice space, and that is what I'm now going to study instead of C itself. Now, up to homotopy, if I'm just interested in homotopy type here, I will lose some information. The question is just how much information can I retain about the category. But notice here's a very nice map. The morphisms from my category define for me a map, a map from the interval into my classifying space. Why is that? Well, I guess I'm given A and B are the same, so I can just take the morphism F now, which will now be a loop because A and B are identified. So really, every morphism gives me a loop in my classifying space. Yeah? And it's that map that one is interested often to understand how closely it is in equivalence up to homotopy in homology, etc., etc. So it's a very important map. But notice, somehow we really lost some information because up to homotopy, of course, every one of these paths is reversible. If F went from A to B, well, in the space, there's no reason why I can't go from A to back to B. And any path I can reverse in topology. That's no problem. So really, we are somehow inverting all the morphisms up to homotopy when we're looking at the classifying space. That's another thing to take on. Okay, so there's a little bit of general nonsense. Monoidal categories, if you have a tensor product, a product on the category, then you have a product on the resulting space. And if this product is even symmetric monoidal, basically commutative, then what you get is an infinite loop space, something, those of you who have seen operas, that's totally in infinity space. So let's do this now with our large category, cobordism category. So we had this category here, a corp D. Remember, it was manifolds of dimension d minus 1 embedded in some large Euclidean space, and then the morphisms were all the cobordisms between two such manifolds, and they could vary. Right? So big topological space. And the identification here is given again by a bit like in Tom's theory, by a big space, which looks a bit scary at first, but the ingredients are very well known. And indeed, let me just tell you what they are. The UDN is exactly the thing that we had in Tom's theory, namely, we have a start off with Grassmannian manifold of d-dimensional planes in R, d plus n, and this is the universal d-dimensional bundle over it. And now we have to just take the complement. That's the difference. The perp means I take the orthogonal complement of that bundle. Okay? So not much different. I take compactification of this orthogonal complement. And again, I take maps from a sphere into that, just as before. Only notice I shifted by d, and that's this comment here. The so-called Tom class is now in negative dimension rather than positive dimension. But that's not so. So what is the characteristic map? I said, every morphism should give us actually an element in here. So, and that's just a generalization. This map is now just a generalization of what we did here. So remember, for configurations, we just taking a few points, take a neighborhood, collapse everything outside the neighborhood, and you get a sphere, and then map over. So in this case, we just do something very similar. Only you take a surface, you take a neighborhood of it. This is still sitting in n plus d now. You take its compactification, and now you can see why we have to have a shift up here. So we're here, and then I collapse the neighborhood of my w. This is w, this is n of w. Collapse the neighborhood, and then I just push it forward by the classifying space of the tangent space of w. That's what's happening. And that gives me, that is the characteristic map in this case. So, if you like, here we are talking really about a map of moduli space or configuration space of w's into this rather large space here. Now, as before, I showed you the calculation in Tom's case, which came down to a theorem of Serre, really. The rational cohomology of these spaces are very well understood. And again, the same ingredients come in. We have the dimension shift, minus d, and of course this whole thing depends on the cohomology of the Grassmannian, which is a BSOD. So that's an explicit calculation, and it's not very deep, the calculation of the rational cohomology. So just going back one step. So we here have the theorem that I mentioned earlier. I attributed then to Graham because if you look at configuration space in every Rn, then I think it really is his theorem. But more generally, it was also already realized before by Baird, Priddy, and Quill that there's a canonical map from the symmetric group, or the classifying space of the symmetric group, which is a B div of n points, the zero manifold, into this space here, which is the maps from an n sphere to an n sphere, and then just let n go to infinity. And that is an isomorphism in homology for degrees less than n over 2. And then Matz and Weiss were able to prove the similar result for surfaces. And again, as this is an isomorphism in certain degrees, and in particular, it tells us that this mg is actually up to rational homology the same as this B diff, and it's a moduli space of Riemann surfaces, and that becomes now just a polynomial ring by our earlier calculation up to certain degrees. And this can be also generalized. Randall, Williams, and Garfish generalize this for higher dimensional manifolds. Okay, so I'll say one more. I have one more slide, I think. And what I want to say is a little bit about how this calculation now connects back, maybe, or what it says in respect to the cobordism hypothesis. So remember, well, two things I should say first. This space infinity, omega infinity, S infinity. And that's a very important space for stable homotopy theory. Basically, it's a ground ring in stable homotopy theory. So it's a Z for rings up to homotopy. Okay? So it's a very important ring. But it also has similar properties like Z. If you have a map from Z into any other ring, then you only have to know where the identity goes, right? Once you know where one goes, you know where the ring map is determined. The same thing is true for this space omega infinity, S infinity. Once you know where one point goes, the non-base point, the whole map is determined, as long as it's a map of infinite loop spaces. So it's a map of rings up to homotopy. So that's one thing to keep in mind. And let's go also. That's not what this is. So the other thing, remember, once we associated a classifying space to the category, all the morphisms were inverted up to homotopy because a morphism got an interval, and an interval doesn't have a direction. You can go either way up to homotopy. So if we look at something that is actually, a TQ of T in the sense of Lurie and Hopkins, this extended one, and we look at the framed version of it, when it is actually invertible, so we have this functor. And it also has to preserve the product structure. Disjoint union was supposed to go to tensor product or whatever symmetric monoidal product I have now on this bigger thing. So that means immediately, if I now look at this functor and look what it happens on classifying spaces, that map it induces is actually a map of infinite loop spaces. It preserves the symmetric monoidal structure which led to an infinite loop space, which basically in our context says it is a map of rings up to homotopy. Now, as I'm looking at framed things here, cobordism here, it's well known that that space is actually just our ground ring in stable homotopy theory. So we can see that certainly this map on classifying spaces will be completely determined by what it does to a point, because it is just a ground ring like that, and it will be determined where the unit, where the point, one point goes. So the upshot then is that you can also think of anything that is determined by what happens on the classifying space as an invertible TQ of T. So really, this little calculation tells us that if F is invertible, then it will factor through B of F, but it will in particular be determined by what happens to one point or either in the category or in the space. So in some sense, this gives you a little proof of the cobordism hypothesis for invertible theories, if you believe my theories beforehand. So I'll stop there and take any questions.
Thank you very much. Any questions?
Could you describe, I don't know if this makes sense, any examples of these extended TQFTs?
Yeah, well, that is a very big research problem. I can write down examples which are sort of coming from the definition, and you would think, well, what's the point of that? Let me see. You certainly can do it, of course, for, I've done it for the zero-dimensional case, but now you would like to see it maybe for the next level up. I probably can do it for invertible ones, but that's not very deep. The problem is really to write down examples, and I think you're a completely fair question, and I think it is actually an active research, should think of research area. The problem is really to come up with good definitions of this thing. Okay? So in the zero-dimensional case, 0 plus 1, or yeah, we just had it as a category of vector spaces, which we understand. One level up, people thinking about maybe taking rings and modules and bimodules and so on. And again, that is already not so easy. The problem being, I mean, in a way, it's beautifully easy once you are happy with n-fold. Let's see, what's that here? If you're happy with n-fold categories, then it's this thing that I've written down, this cobordism category, is actually a strict n-fold category. Now, there are not many of those. And strict n-fold categories that you would want maybe over here are very hard to come by. So, and the non-strictness is a problem, really. It's a problem for coming up with nice examples. It's not a problem in this context because you allow yourself, in some sense, with the topology to have non-strictness. And that's why the reason why you had to go to this bigger category. But yeah, an easy example is not easily had. Non-trivial, I guess I should say.
Questions? I do have a question myself. The cobordism hypothesis, has there been any attempt of formulating it for Poincare complexes?
I don't know. I don't know. I assume not. Maybe.
I don't think so.
No.
Do you think it would be possible?
Formally, you can certainly define the Poincare cobordism category.
Yes, you can define it. You can maybe even make the conjecture. I have no idea how you might
Prove it.
Yes. I suppose the idea, the problem, well, I don't know, even parts of it, the parts that are more, when you use the configuration spaces of higher dimensional manifolds, just sitting in YRM, that sort of analysis is completely lost. That would also really be lost in the topological world.
Okay, so
And
difficult also for topological variables.
So
Yeah.
not even for topological, even if one drop the differentiability would be a problem.
Yeah, that's fine.
Okay, well, let's conclude that it's not going to be easy.
It's not going to be easy, that's for sure.
Is it finally no more questions? Okay, so let's thank Ulrike again.